Okay, so let's just kind of go through a lot of these questions. How about that? So let's start with, I don't know, number 5. That's one of the more complicated ones, okay? So let's talk about number 5. So when you start off with number 5, and again, every force problem, okay, every force problem can only be one of two situations. Either you're at a constant velocity and all the forces add up equal to 0, or you're accelerating. Okay, that's it. Here's the first thing that you need to figure out is if it's accelerating, what's the force that's unbalanced? If you're at a constant velocity, I make all the forces add up equal to 0. That's it, okay? And if you're a constant velocity, you're adding up to 0. Not pi, not -5, okay? You're just making everything add up equal to 0. So if you look at what's happening on number 5, the first thing that let's say you get this problem, you have, it's like, I have no idea what's going on. Draw a picture so you can see what is going on with the forces, okay? So on this situation, you're always going to have gravity. We're on Earth. You're always going to have a gravitational force pulling down. And as long as it's sitting on a surface, you're going to have a normal force which is pushing up. Okay? So unless you are in free fall or you're in deep, deep space, those are the two forces that are always going to be there. Okay? And gravity is always going to be there unless I specifically tell you otherwise. Unless I tell you the effects of gravity can be ignored. You always assume that the gravity is there, okay? Now, because of the fact that this thing is moving at a constant velocity, so imagine this is this box, okay? I'm pushing it like this, and we're moving along at a constant velocity. Now, here's the other thing that you have to keep in mind, and this goes back to Newton's first law. The only reason you ever have to apply a force to keep something moving is because there's friction. Okay? If you eliminate friction, inertia is just the tendency of an object to maintain a constant state of motion. So inertia will keep it moving. Okay? So what? Inertia will keep it moving. Boom. And if you see something stop, that means there's something opposing that motion because it doesn't want to stop, it actually wants to keep going. So if you see something stopping, you know there has to be a force acting on it. So you've got this force applied and this force friction going in the opposite direction. Add all those together, boom, I'm going to get 0. That's it. Now, what I'm at, and the information that I've given you on 17a, you're told that, wow, here's this coefficient of friction. How much force has to be applied? So you know that force friction equals mu times force normal. Okay, I gave you the value of mu, 0.38. You have that number, okay? What you don't know is the force normal. But if you're on a flat surface, force normal is the same as your gravitational force, which is your mass times your gravitational acceleration. So that answer to 5a should be something very close to your current age, okay? Very close to that. Close to your current age. Just take mu mg. Take mass times mu times gravitational acceleration. There's your force friction. Your applied force is going to be balancing that out. Now, imagine here's this cart. I'm pushing it and I stop pushing it. So why does it come to a stop? What did I lose? Devin, what did I lose when I stopped pushing it? Which of those 4 forces did I lose when I stopped pushing it?
Force supply.
Our force supply, okay? That's no longer there. So what's still there is the frictional mafia, okay? The frictional mafia is going, good boy, I want to slow you down, okay? Because the frictional mafia is going to work in opposition to that movement, okay? So the frictional mafia is always going to be there. So you stop pushing it, it's just like you stop paying money to the mafia. And the mafia goes, you stop paying us money, we're going to make you stop. because now there's nothing to balance out the frictional mafia. So frictional mafia goes, we're going to make you stop. You're a good boy, but we're going to make you stop. So now that becomes my unbalanced force. Just like if I go up behind, I won't do this because I like Hector, but just like if I went up behind Hector and I pulled that chair out from underneath him, he's going to begin to accelerate because there's nothing balancing out, in that case, the gravitational mafia. So the gravitational mafia is always trying to hold you down. The chair is preventing the gravity mafia from pulling you down. So the chair is balancing that out. Your applied force was balancing out the frictional force of mafia. So as soon as you stop that, just like, let's say, for example, you're operating in business and the mafia says, hey, you pay us $1,000 a month. Okay, well, as soon as you stop paying them the $1,000 a month, they're going to shut you down, okay? Not so much in Kansas, but if you go to Chicago, it happens all the time. So now you have an imbalanced force. Now, think this through. So you want to find the acceleration. So when you get to C, you want to find the acceleration. So this big sign back behind you that says force equals mass times acceleration. So the question is which force is going to make you stop? Is it the normal force? Is it the gravitational force? Or is it the force friction? Which one of those three, because those are the only three acting on you at that point. So which one of those three, Bailey Martin, is going to make you stop? The friction, the normal, or gravity?
I was working on part A and I was fixing part A.
Okay. Let's go to this diagram. Okay? Here's the box. I'm pushing it. I stop pushing it. Which one of those three forces is going to make that box stop? Friction, gravity, or the normal force?
Friction.
Friction. So that's what's going to make it stop. This is what we call the net force. This is the unbalanced force. So to get your acceleration on C, take that unbalanced force, which is the friction force, divide that by the mass, there's your acceleration. Now, Peyton, is my acceleration going to be a positive or negative value?
Negative.
Why? With? Right? No. Rhymes with positive velocity. Yes, with positive velocity. So just don't say, oh, I'm going to slow down and my acceleration is negative. Your acceleration is negative because you have positive velocity and you're slowing down. So, because of the fact that if you're defining forward as being positive, which is cool, that means your frictional force is going to be a negative value acting in the opposite direction. So your answer to 5C should make a fairly decent GPA. Okay? Not horrible, but not bad. Right? Now, when you get to E, when you get to D, you want to figure out how far this thing is going to go. Well, look at this. Here's your velocity time graph. You're going to move at a constant velocity at 5 meters per second for 6 seconds. So right away, how far are you going to go during that time? You're moving at 5 meters per second for 6 seconds. Jack, how far am I going to go?
30 meters.
30 meters. So I'm at 30 meters at this point, okay, which is about a third of the length of the football field. So I have already traveled 30 meters, okay? It's 30 meters. That 6 seconds is how long it's being pushed at a constant velocity. That isn't how long it's taking to slow down. That's how long that has moved at a constant velocity of 5 meters per second. Okay? Cool with this. Got it. Good. Great. Now, at that point, I stop pushing the block. Bailey Martin, I stop pushing the block. What's the only unbalanced force? I stop pushing the block. What's going to make it slow down?
Friction.
Friction. Thank you very much. Now, we just said, oh, that's going to cause an acceleration, which is your answer to C. Now, you don't know how long it takes to stop. Okay? You don't know that value. It isn't the 6 seconds. I'm not telling you it took 6 seconds to stop. You don't know how long it takes to stop. But Do you know the initial velocity? Oh, that's 5 meters per second. You know the final velocity, that's 0. Now you know the acceleration because that's your answer to 5C. So this graph is going to go doink like this. Okay, that's what's going to happen. You don't have to find the time, okay, but you know that's going to be the general shape of it. And you know the slope of that line is going to be your acceleration that you just found on 5C. So when I'm talking about this net force, the net force is the sum of all of the forces. So when you have a horizontal line on a velocity time graph, this is where like A equals B, then B equals C. If you have a horizontal line on a velocity time graph, that means you have no acceleration. That means the sum of the forces is equal to 0. The net force is equal to 0. Okay? So there's forces acting on it. You're just not accelerating. Then I stop pushing it. Bailey Martin just told me twice that the net force or the imbalanced force, which means the same thing, is the friction. So that unbalanced force on this part is going to be that negative 17.9 newtons, because that's the force that's unbalanced, and that's what's making it accelerate. Because the frictional mafia is not being balanced out. The frictional mafia now is going to make you stop. Okay, it's like, whoa, 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 you got to stop. And the acceleration is going to be the slope of that line. Okay, so on 5E, that's what your graph is going to look like. But make sure you label the net force. Make sure you've labeled the acceleration in each section. So when you have a horizontal line on a velocity time graph, there's no acceleration because there's no unbalanced force. If you have a sloping line on a velocity time graph, that means you're accelerating. That means that there's some unbalanced force which is making that cart accelerate. Okay? Cool with that one. Okay, on number 4 with the question with the balloon. Okay? So here's your scale, and I happen to have a hydrogen fuel. Okay? So if I let go of this thing, it accelerates upward. Okay? There's a buoyant force that's acting up. So imagine this. So here's this mass, right? It's just going to sit here on this book. So right now, gravity is pulling it down, and the book is providing an upward force which is balancing everything out. Now, I take this balloon, and I hook it to that mass. What do you think is going to happen? Imagine that I have a little scale here. What do you think is going to happen to the reading on that scale once I hook up the balloon? Is it going to increase, decrease, or stay the same? Hector.
The number of the scale?
Imagine that I have a scale here.
Yes.
It was reading a certain number. I hook up the balloon. What do you think is going to happen to the reading on that scale?
It's going to decrease.
Huh?
Decrease.
Yeah, it's going to become less because gravity is still pulling it down, but the balloon is providing some upward force. Now, here's the question. Is that accelerating? Yes or no? No. So what does that mean? All the forces still have to add up to 0. Okay? Now, by hooking up the balloon, did I change the Earth's gravitational pull on the mass? When I hooked up the balloon, did that change that? No, it's still the same. Okay? Just like if I hold this, okay, if I just sit here and hold this, okay, I'm not going to go floating up, okay, which would be kind of cool, but I'm not going to go floating up. Gravity is still pulling it down. Now, is this providing a little bit of upward lift for me? Yeah. Okay, not enough to make me go up in the air. So, again, it goes back to this idea that if it's not accelerating, make all the forces add up to equal to 0. So when it was just sitting there, you only had 2 forces. you had gravity, if you want to define gravity as being down, okay, then that's going to be a negative 4.9 newtons, and the scale was providing an upward force of 4.9 newtons, and everything would add up equal to 0, and it's cool, okay? Now, I hook up the balloon. This drops to 4.8 newtons, okay? So if you want to think of it in terms of money, okay? I owe Angel $4.90, okay? Right? It's like, hey Angel, I need to go buy a physics thing. Angel loans me $4.90, okay? I pay him back $4.80. How much do I still owe Angel? 10 cents, because everything still has to add up to where we started, right? So that means that balloon is providing an upward force of 0.1. Everything still adds up to equal to 0. 0.1 plus 4.8 plus a negative 4.9, everything still adds up to equal to 0. Okay? Cool with that. Let me see. All of your answers on number 2 should be somewhere between 4 and 10. Make sure you have the correct number of significant digits, okay? Let's say, for example, I'm just going to say hypothetically, let's say your answer to 2A, let's say you just have an answer of 4, okay? How many significant digits are in the number 4? 1. How many should you have? 3, okay? So what are you going to have to do? Yeah, make that 4.00. I'm just saying hypothetically. That might be your answer to 2A. It might not. I'm just saying. All of your answers on 6, 7, and 8 should be something times 10 to the third. All of your answers 6, 7, and 8 are all 10 to the third. Your answer to number 9 should be something times 10 to the fifth. Now, let's talk about number 10. So, on number 10, you have 2 different masses, okay? So, because if 10A starts wrong, everything's going to go wrong. So, your first gravitational force on 10, one force should be around 4, the other one should be around 8, okay? So, those are those 2 forces. So, when you talk about inertia, which is this answer to B, inertia is only determined by one thing, and one thing only, and that's the amount of mass in the object, okay? So the more mass that you have, the more inertia that it has, the harder it is to get to move, but once it gets moving, the harder it is to make it stop, okay? So yesterday when I got smashed with the block, the reason that I didn't completely accelerate and get impaled by those nails is because I had a large amount of mass, okay? I had a large resistance to a change in motion. Okay. Any other things you want me to go over at all? On the board? Yes?
Like C and D on 10.
Okay. So if you look at those questions, so on 10C, here's the story. So imagine this. Here's this object. I drop it. As soon as I drop it, what's the only force acting on it? Which is your same answers to, so your answers to 10C are the exact same answers as your answer to 10A. Because once I drop it, that's the only force acting on it. Now, here's what I want you to see, and we'll spend more time talking about this. Is that, let's say for example, I've got Hank, and I got this ball of twine, okay? And I drop them. Here's what I want you to see. Is that obviously, if here's Hank, there's Hank, okay? And there's this ball of twine. If I drop them, there is a lot more force acting on Hank than there is on the twine. There's a lot more force acting on it. But Hank has a lot more stuff inside of him. So it's harder to get Hank to accelerate because Hank has more mass, Hank has more inertia. So when you drop things, everything accelerates at the same rate. Not because it's the same amount of force, but it's because that force is proportional to mass. So this is why, if you look on that very first graph that you did, problem number 1, okay, that graph is going to look like this. Okay? The more force, the more mass there is, the more it weighs. But the more it weighs, the more mass it has, the more inertia it has. So I have to have more force acting on more mass to end up with the same acceleration when I drop things. So I want to get this out of your minds right now. Don't say, oh, gravity is the same for everything. No, it's not. No, it's not. There is a lot less force acting on this ball of twine than there is on Hank. Okay, there's much more force acting on Hank. But I have to have more force acting on more mass to end up with the same acceleration when I drop something. Okay? Cool with that. Anything else? Going once. Let me give you a hint on those multiple choice questions on 5 through 10. You should not have an answer of B. Okay? So on 5 through 10, there is no answer for B. Now let's talk about question number 4. So on question number 4, I explicitly tell you to mention Newton's first and third laws of motion. Okay? So basically, here's what I'm looking for. Do you understand that when you're sitting there in a plane, your body has mass? Your body wants to remain at rest. Okay? So when that plane begins to accelerate, your body wants to stay at rest. Okay? The seat is pushing you forward. Okay? So you feel like you're being pushed back in your seat. Okay? It's not what's happening. There's no force in front of you pushing you back. Okay? It's not there. What happens is that your body wants to stay at rest. The chair pushes you forward. Newton's third law says that, I'm going to push back on the chair with an equal and opposite force. So there's nothing pushing you forward. You just want to stay at rest. The chair pushes you forward. You feel that action-reaction force of you pushing back on the chair. Okay, there's nothing in front of you pushing you into the chair. It doesn't exist. Okay, anything else? Going once, going twice, sold? Okay, get those handed in. Can you stop that camera for a second? Thank you. So, if I had to make a list of like some of the most important concepts that you really need to get out of this class, this idea of net force would very much be up towards the top of that list, if not at the very top of the list. Because it's going to play out in terms of so many things that we're going to do going forward. So, what I did is that I wrote this story, and kind of to get you an idea of in a different context. So y'all are horrible at reading, and your odds are you're not going to read it anyway. So I'm going to read it to you because I wrote the story, and it's a good story. And I'm going to read it in a horrible British/Scottish/Australian accent. Okay, so I'm just going to tell you that right now. I'm going to try, but bear with me. All right. So, once upon a time in the kingdom of physician, there were two opposing forces. One represented the forward-looking people who wanted progress, and they were very positive. The other was the faction that opposed everything that the positive people wanted and were generally considered to be negative. Thus, in the kingdom, there was always a struggle between the two forces. The positive people had a variety of tools they applied in their battle. They could push, shove, lift, throw, hurl, heave, and once they discovered mechanized equipment, they started using rocket engines and hot air balloons. Theirs was viewed as a positive force since they were trying to move the kingdom forward. In opposition to such forward-thinking endeavors, there was the negative people who opposed anything that the positive people would attempt, and they were negative. Okay, let's try thinking that was horrible. You had one audience participation line. Boo, yes. Let's try this again. Okay. So people who oppose anything the positive people would attempt, and they were negative. Nice, nice. That's good. I like that. Okay. Hey, back into character. Okay. As with the positive people, they too had a variety, various tools at their disposal, but they were limited to only two tools, friction and gravity. The friction and gravity were generally referred to as the opposing forces and took away from the endeavors of the forces applied by the positive people. In future years, they would become known as the Gravity and Friction Mafia. The negative forces could also only be used in special circumstances. If the positive people were trying to move something horizontally, then the negative people would use friction to oppose the applied force. The more friction there was, the less positive force remained, the more money paid out to the frictional mafia. The positive people were trying to get something into the air, vertical motion, then the negative people would use the weight calculated by taking mass times gravitational acceleration. The more massive the object is, the more money paid out to the gravity mafia. As is true of every epic battle, protocol had to be established to determine who won or lost each battle. After much wailing and gnashing of teeth, it was determined to use the mathematical system of this equation. So here's the mother of all physics equations in terms of this force unit. Now that's force net equals force applied plus force opposing. Okay, literally. Now on, you view every problem through this lens, through this equation. Okay, literally, this is the basis of everything that you're going to do. Now, the beauty of this is that there's only two things that can happen to force net. And there's only two things that can happen to force net. If your force net equals 0, that means that acceleration equals 0, which means that you have constant velocity. Okay? Now, if your net force is equal to 0, that doesn't mean that there aren't forces acting on the system. It just means that everything adds up to equal to 0. So right now, if I look at this little mass that's being lifted up by the balloon, okay, it sits there. Right. All the forces add up to equal to 0. I'm not saying there aren't forces. There's a whole bunch of forces going on. The balloon is lifting up. You have the table providing some upward support. You have the gravitational field trying to pull it down. So there's three forces acting on this dynamic. They just all add up to equal to 0. That's all. No, your alternative is your force net does not equal to 0. That means that your acceleration is not going to equal 0, which means that you're going to change your velocity. Now, notice that I did not say that your velocity is going to increase. All it means is your velocity is going to change, right? It might get bigger. It might get smaller. It might change the direction of it, okay, once we get into circular motion. So that's why I said every problem that you're going to have can only fit in one of two slots. Either the net forces equals 0, which means all the forces adding up equal to 0, or it doesn't, and you begin to accelerate. That's it. There's only two games in town. That's it. All right. So let's say for example, I take this balloon, and I'm going to put a small little binder clip on it. Okay, and then I want to let go of it. Okay. So I got this action. So I've got the small little. Okay. So here I got this little binder clip. Okay, it's even blue. Thank you. And I'm going to let go of it, and this thing is going to begin to accelerate upward, right? So if I look at this in terms of acceleration, okay, so here's the balloon, there's the binder clip, okay? I let go of it. Which direction does it accelerate? Let's just start with this idea. It accelerates. Which direction does it accelerate? Upward or downward? Up. So here's the other thing. Force net equals mass times acceleration. Your force and acceleration have to have the same sign because mass is never negative. So if you're defining up as positive, which is cool, you could also define up as being negative if you wanted to, but let's just define up as being positive because that's what most people want to do. So when I let go of this, that tells me that the net force acting upward is positive, and then my acceleration is also going to be positive. So when I let go of this thing, whatever the force is, that applied force from the balloon has to be bigger than the gravity mafia that's pulling it down. Okay? The difference between these two is my net force, and my net force tells me the direction of the acceleration. So there's a couple of different ways you can view these net force problems. And again, the more ways that you can think through a problem, the better off you're going to be. So, okay, hey, I let go of this thing. Start with that idea. My net force has to be a positive value. Oh, that means whatever my upward force is has to be bigger than whatever my downward force is. So my positive force is bigger than the gravity mafia that's trying to hold it down. Okay, that's why it accelerates upward. The other way that you can do this, and I highly recommend, if not almost force you to do this, is to set up a chart where you're going to go force applied, force opposing, force net. Okay? Start with this idea. So I don't know the numbers, but here's what I do know. I know my applied force is going to be some positive number. I don't know what it is. I don't care what it is for now. I just know my applied force is going to be some positive number. I know my opposing force is going to be a negative number that is less than my applied force. Okay? So when I add these together, when I find the sum of these, I know that I'm going to have some positive net force which is acting upward. Okay? So as soon as you see something accelerate, you know right away, your net force is not going to equal zero. That's it. Okay, it's not going to equal zero. You're going to begin to accelerate. Now, mathematically, force net equals two things. That was horrible. Force net equals two things. It equals force applied plus force opposing. It also equals mass times acceleration. Okay, so it equals two things. So right away, as soon as I see something accelerate, I know that my net force is not going to equal to zero, and if I want to find the acceleration, I'm going to take the net force and divide it by the mass, boom, that's how I'm going to get my acceleration. Now, let's change it up a little bit. So I'm going to put another binder clip on here, okay? So now I put another binder clip on here. So what happens to the rate of my upward acceleration? It's decreased, right? So here's the story. And this is hugely important if you ever want to be like a rocket scientist. Okay? This applies to rocket science. Force opposing, force net. So this is when I have two binder clips hooked up to the balloon. Okay? Now here's what I want you to think through. I put a second, so let's get a visual, okay? So there's my one binder clip acceleration, okay? Here's my two binder clip acceleration, okay? So clearly, which one's bigger? One binder clip or two binder clips? One. Clearly, that's bigger acceleration. So when I have two binder clips, this is what you want to think through. When I put on that second binder clip, what did that do to the upward force created by the balloon? Did it increase it? Did it decrease it? Or did it just stay the same? Izzy?
Repeat.
Huh?
Repeat.
Okay, so here's my first binder clip, right? Here's my second binder clip. When I put on the second binder clip, what did that do to the upward force created by the balloon? Did it increase it, decrease it, or did that just stay the same?
It stayed the same.
Stayed the same. Because the balloon doesn't care. okay, that balloon is going to be providing some upward force. The balloon doesn't know what's happening down here, okay? The balloon just knows that, oh, it's a buoyant force, it's going to act up. So whether I'm at one binder clip or not, so let's do a little side-by-side comparison. So there's one binder clip, there's two binder clips. My applied force in both situations is going to be some positive number, okay? That's not going to change. That's going to be the same for both of those, okay? Now, my opposing force. My opposing force is either going to be the frictional mafia or the gravity mafia, okay? That's it. So, Jaden, what am I working against? The gravity mafia or the friction mafia?
Gravity.
Okay, gravity mafia. Now, when I put a second binder clip on here, what do you think happened to the amount of money I have to pay to the gravity mafia? Did it increase, decrease, or stay the same?
Increase.
Increase. Because gravity mafia is going, you want to move two binder clips, huh? That's cool. Oh, happy for you. Well, you need more money. Okay? So the more mass that you have to lift, the more influence the gravity mafia wants to have. It's like, that's cool. You want to move more stuff? You got to pay us more money. Okay? Because that's what the gravity mafia does. So, and if you look at how you calculate how much you pay the gravity mafia, this is the formula that the gravity mafia uses. The gravity mafia says, this is how we're going to calculate how much money you owe us. We're going to take the mass that you want to lift, and we're going to multiply that by 9.8 meters per second squared. That's how they're going to calculate their money. Okay? That's it. More mass that you have, the more money it's going to take to get this thing that they're going to charge you. So I have, by putting on a second binder clip, I've doubled the amount of money I have to pay to the gravity mafia. Okay? So with that opposing force, with one binder clip, that was a certain number. Okay? I don't know what it is, it's a certain number. But with two binder clips, now that's got bigger. Okay, so now I got to pay more money to the gravity mafia. But Izzy just told me that the buoyant force upward is going to stay the same. So think about this. Okay, it's like a money transaction. You're going to sell a widget, okay, a generic thing, a widget, for $10. In the first situation here, it might only cost you $2 to make the widget. So you're selling it for $10. It costs you $2 to produce the widget. You're going to have a net profit of $8. Okay? You're selling it for $2. Selling it for $10. It costs you $2. You have a net profit of $8. Now, situation number 2. You're still going to sell the watch or the widget for $10, but it costs you $5 to make the widget. So now your net profit has gone down because it costs you more money to make the widget. So what's happening here is that as I increase the money that I have to pay the gravity mafia, I have less money left over. So there's two important things that are going to happen right here. This is going to be some positive net force that's acting upward. Okay? And I know that because that's the direction that it accelerates. When I put two binder clips on here, Connor, what's going to happen in my net force when I put that second binder clip on there?
It goes down.
It's going to go down. So I'm still going to have a positive net force, but that's going to be a much smaller number because I had to pay more money to the gravity mafia. Okay? Now, here's the second thing that happens. So when you look at force net, okay, and I'm going to look at two different situations. The one binder clip and the two binder clips, okay? If I were to compare these two, this is where this has like a double impact, okay? So when I have one binder clip, I had a bigger net force, right? And that was mass times acceleration. So to get this acceleration, I'm going to take that force net, and I'm going to divide that by a certain mass, and I'm going to get an acceleration. Now, when I put on the second binder clip, there's two things that are going to happen. Number one, I'm still going to have a net force, but that net force is going to be a smaller net force than what I had with one binder clip. So my net force has gone down, okay? Because I got to pay more money to the Gravity Mafia. But here's the second thing that happens. Not only do I have a smaller net force, but now I'm going to divide by a bigger mass, okay? Because now I have more stuff to move. Because now I have to lift two binder clips. The first one was just one binder clip. I didn't have as much stuff, okay? Now I have more stuff, okay? So I have more stuff to move, but I have a smaller net force. So this is why when you're trying to get something up in the air, you're very, 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 very concerned about the mass that you have to lift. Because as you increase that mass, you have two effects. As that mass gets bigger, you get a smaller net force, but then you have more stuff to lift, so you're dividing by a bigger mass, so you have a smaller net force on top, dividing by a bigger mass down below, which is going to make that acceleration become less. So if you were to look at this like on a velocity time graph, okay? So here's this velocity time graph. So let's say that's my velocity time graph for one binder clip. Okay? This is my one binder clip. Going to have positive acceleration, it's going to move up. So if this is my one binder clip line, Jack, what's my two binder clip line going to look like? The exact same, steeper, more shallow.
Shallow.
Why?
Because because the acceleration is a whole lot smaller.
Fantastic. So this is my two binder clip line. Okay? Cool with that. Now, let's I'm gonna put a little paper clip on here. A little paper clip on here. Now I'm gonna let go of it. So is my net force still pointing upward? But is it very big? No. So at this point, I barely have a positive net force. Okay, it's just tiny, right? Because again, by putting on that paper clip, by putting on the binder, when I put on the paper clip, what did that do to my upward force from the balloon? Nothing. That stayed the same, right? Go away. So, but what did I do to my opposing force? What did I do when I put that on there? What did I do to my opposing force? Increased it, decreased it, or stayed the same? Increased. My net force became smaller, but my mass increased, so now this one is just basically very, 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 very shallow. Okay? Now, if I could hit this just right when I let go of this, if the two forces, which is basically what's happening right now, hydrogen is very, very, the reason that my balloon is I'm actually losing my my buoyant force over a period of time, because hydrogen is really, really small and it's actually escaping through the balloon, okay? So now when I let go of it, I've actually, during this short amount of time, I've lost enough hydrogen out of that balloon that now when I let go of it, my net force is now actually pointing down. So, now what's happening? Now what's the direction of my net force?
Down.
Down. Because I've lost hydrogen from this balloon, even though to us it looks solid, on an atomic level, these hydrogen molecules are escaping out, and I'm actually losing that buoyant force. So now, when I let go of that, my net force is actually going to point downward. So now, I have the same amount of gravitational force. I haven't changed that. But because of the fact that I'm losing hydrogen, my buoyant force has become less, and now my net force points downward, and now my velocity time graph would actually have a slight negative slope to it. And so, if I let this sit there all day, by the end of the day, that balloon is going to be about half that size, because that hydrogen is bouncing around and it's so small it's actually escaping out through the balloon. So give this push. Boom, it's going to stop. So this is like watching gravity in slow motion. So this would be like imagine that our gravitational field was really, 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 really weak, and you throw something up in the air, and that would be the acceleration, okay? So everything would be like in extreme slow motion. Okay, so here's how this also plays out. So this is why I like to teach physics, because I get to go to Dr. Botts and go, hey, I need toys. And he's going to say, why do you need a remote control helicopter? Because I need to teach net forces. Okay, so here's my helicopter, right? Turn this on. Turn this on. Okay, now, so when that helicopter is hovering, okay? When that helicopter is hovering, are there forces acting on the helicopter? Yes, but when it just hovers, just like that, what do you know about those forces? They're equal and opposite, right? So what I'm controlling with the lever, stuck it. Okay, so when I adjust the power, when I adjust that power, what am I changing? My applied force, my opposing force, or my net force? What is this button control of those three? My applied force, my opposing force, or my net force? Yeah, I'm changing my applied force, right? That's what I'm changing. Now, if this helicopter, here's this helicopter, right? Okay, that was my helicopter. So it has a certain amount of downward force. The Gravity Mafia is sitting there going, hey, that's a good boy. You want to get your helicopter off the ground? You got to pay us off. So there's a certain amount of downward force, right? Now, if I'm going to make the helicopter get off the pad, what do you know about my applied force relative to my opposing force? This has to be bigger or smaller than my gravitational force. Does my applied force have to be bigger or smaller than my opposing force? Hector?
To make it go up,
Yes.
like the one that goes upwards.
Yes. Yes, it has to be bigger, right? So if I just turned on the helicopter, okay, and I don't provide enough upward force, it's not going to fly off the table, right? So if I want it to accelerate upward, I have to give it enough force so that the upward force going up on the helicopter is bigger than the downward force pulling it down. If it's just hovering, those two forces are balanced out. If I want it to accelerate upward, I give it more throttle. If I want it to accelerate downward, I give it less. And if it just balances out, those two forces are going to completely balance each other out. Kind of crashed, but not bad. Okay, got the idea. So let's say that we want to do rocket science. Okay, literally, let's say we want to do rocket science. Lost even more hydrogen. Okay? And let's say here's a rocket. And let's say that it has a mass of, 2.04 kilograms. Bailey, pick a number between 20 and 30.
25.
And we're going to have an applied force of 25 newtons. Actually, I want to make that 35. I should have told you between 30 and 40. Let's make it 35. Okay? So here's the story. So this is going to play out in the story problem. I'm going to tell you a rocket sits on the launch pad. It has a mass of 2.04 kilograms. The engines can provide an upward force of 35 newtons. I want you to calculate the acceleration of the rocket. Now, here's the first thing that you have to do, okay? The first thing that you need to ask yourself in a question like this is, do I have to pay off the mafia? Do I have to pay off the frictional mafia, or do I have to pay off the gravity mafia? Okay? So in this situation, here's this rocket, right? Boom, sits on the launch pad. You want to make this thing go up in the air. So which one do you have to pay off? The frictional mafia or the gravity mafia? Gravity mafia, okay? Unless I explicitly tell you to not worry about gravity, unless I explicitly tell you that, you think through and you go, wow, I got to pay off the gravity mafia, okay? Always do that. Unless I tell you, you're in deep, 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 deep space where the effects of gravity can be ignored, you pay off the gravity mafia, okay? So, I beg of you, get in this habit of making this chart. Going, here's my applied force, my opposing force, otherwise known as the mafia line, and then your net force, okay? So in this case, is my 35 newtons my applied force, my opposing force, or my net force? Miss Coleman.
Applied.
Yeah, so I got 35 newtons, okay? So what you have to figure out is, like, Devin wants to start a business. Devin has $35. We got to figure out how much money Devin has to pay to the mafia so we know how much money he has left over to start his business, okay? So the mass of the rocket is 2.04 kilograms. So how can I figure out how much money I have to pay the gravity mafia? What am I going to do? Carson, what am I going to do?
Multiply to your mass times your acceleration.
Fantastic. And how the mafia works is the mafia goes, for every kilogram of mass that you have, we're basically going to charge you $9.80. If you like a monetary example, okay? For every 1 kilogram, that's $9.80. Okay? So I got about 2 kilograms, so I'm going to have to pay off the gravity mafia with about 20 bucks. Okay? Ballpark answer. So, Peyton, do us a favor. To figure out the payment to the gravity mafia, take 2.04 kilograms times G, and what'd you get?
19.99.
So let's just call it 20. Okay? So I'm going to make that negative because that's in the opposite direction. So when you talk about forces, you always talk about the sum. Okay? Never talk about differences. You always talk about the sum of the forces. So down here, this net force is the sum of all the forces. So here's an analogy. Devin wants to start a business. Devin has $35. He's got to pay $20 to the gravity mafia. How much money does he have left over? 15, right? Because that's the difference between, he's got 35, he had to pay $20 to the gravity mafia, he's got $15 left over. Okay, that's his net force, that's his net profit, that's what he has available to start his business. Now our ultimate goal is the acceleration line. Okay, so your acceleration is always going to be your net force divided by the mass to get your acceleration. So Peyton, do us a favor. Take those 15 newtons and divide that by 2.04 kilograms.
7.35.
7.35 meters per second squared. So that's going to be the acceleration of the rocket once I pay off the gravity mafia. Now, an interesting thing. Let's say that I take that same rocket, but now I'm in deep, 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 deep space. Deep space. There's no effective gravitational field. Okay? There's always going to be gravity, but it's just not enough to worry about at this point. So if there's no gravity, what's going to happen to my opposing force? What will be that value? Do not make this difficult. 0, right? There is no opposing force. So if there is no gravity, now, Peyton, do us a favor. Take 35 newtons, because that's going to become my net force. Take 35 newtons and divide that by 2.04. What do you get?
17.16.
17.16 meters per second squared. So what's happened to my acceleration? It's gone up, because now I don't have to pay the gravity mafia. Okay? Now, interesting thing happens. Let's say instead of that mass being 2.04 kilograms, let's say we find a way to reduce the mass of the rocket. Maybe we go from choosing a metal piece and we substitute it with a plastic piece. Okay? And let's say the mass of that rocket drops to 2 kilograms. Okay, I'm going to drop the mass of the rocket to 2 kilograms. Okay? Now, Izzy, I'm going to drop the mass of the rocket to 2 kilograms. What's that going to do from the force from the rocket engines? Is it going to increase it, decrease it, or is it going to stay the same? It's going to stay the exact same, because it's the exact same rocket engines, okay? Just like it was the exact same balloon. Okay, that's why. Okay, so the force of the rocket engines is going to stay the same. That's going to stay at 35 newtons. But what's that going to do to my opposing force with less mass? That's going to become less, because I don't have as much mass. Okay, gravity mafia isn't going to charge me as much because I have less mass. Okay, now Peyton, do us a favor. Take 2 kilograms, multiply that by 9.8. You should get 19.6, I think. 2 times 9.8 gets you 19.6?
Yep.
Okay? So now, I have the exact same applied force, but now I have a smaller opposing force. So what's that going to do to my net force? Carson, same applied force, smaller money that I have to pay to the mafia. What's that going to do to the amount of money that I have left over?
Increasing.
Increase it. So now, take 35 minus 19.6.
15.4.
15.4 newtons. Oh, now, look what happens. Now I have a bigger net force. It's gone up to 15.4 newtons. Now, one thing. Take 15.4 and divide that by 2 kilograms.
7.7.
7 point what?
7.
7.7 meters per second squared. Look what's happened to my acceleration. I have the exact same applied force, but by shrinking the mass, I decrease the opposing force. By decreasing the opposing force, I get a bigger net force, but then I'm dividing by a smaller mass, which makes my acceleration even bigger. So this is why, if you go back and look at the history of the space race, it was the Apollo missions that got us to the moon, okay? Apollo 1 through Apollo 17. They paid engineers that were designing the rockets. The engineers that got the biggest bonuses were the ones that found a way to safely reduce the mass of that rocket. Okay? That's who got the biggest bonuses, because they were so concerned about the weight of that rocket, because the engines can only provide so much force. So, and they had to achieve certain accelerations and certain velocities to put this thing into orbit. So the engineers that could come up with the most cost-effective ways to reduce the weight got the biggest bonuses. And because they lived and died by this formula. If you're a rocket scientist, literally, you wake up every morning and you go, force applied plus force opposing equals force net. And so you either make, if you have to sort of get a payload into orbit, you either have bigger rockets or you decrease the weight of the rocket. That's it. So they're the only options. But it becomes a catch-22. You go, oh, let's design bigger rockets. Well, what's the problem with bigger rockets? Bigger rockets weigh more. Bigger rockets carry more fuel. Bigger rockets have more inertia. The fuel has more inertia. So you say, well, let's just build bigger. Well, that's fine. It's great. But unless the bigger rocket engines produce more acceleration, there's no point in building them because it's a zero-sum game. Okay? All right. Got that. Cool. Now, let's talk the friction mafia. Okay? So let's look at two situations. Situation number one, I'm going to give this car a push with the wheel sides down. Okay? Now, I take this same cart, I give it a push, but then it's flipped over. Okay? So now we're going to be dealing with the friction mafia. So here's the wheels, side down. Here it is, wheel sides up. I'm going to have the exact same applied force. Okay? That's going to be the exact same. So that applied force is similar to the rocket engines. Okay? Something's going to make it move. So I'm going to have the exact same applied force. I'm going to set up this chart. I'm going to have force applied, force opposing, force net. Okay? So I'm going to give this thing a push to make it move with the wheels down. And then this one is going to be with the wheels up. Okay? Flipped over like this. All right? So in both situations, I'm going to have the exact same applied force. Okay? That's going to stay the same on both of them. In which situation is the gravity mafia going to exert more influence? With the wheels down or with the wheels up? Which one's going to be more impacted by the mafia? Wheels up, wheels down? Wheels up, right? There's a lot more friction. So with the wheels down, my opposing force is going to be a really small number. Okay? So I'm not going to have to pay much money to the frictional mafia with the wheels down. So that means I'm going to have a relatively large net force. Okay? Now, I flip it over. I push it with the exact same applied force, but now my opposing force is a much bigger negative number. Okay? Because if you consider your applied force to be positive, my opposing force is going to be a negative number. So what's going to happen to my net force? Like this. What's going to happen to my net force? Bigger or smaller, stay the same? Derek. Wheels are up. Yeah. I'm going to have a very small positive net force because of the fact that now I have to pay so much money to the friction mafia. Okay? So, now, when I look at my acceleration, look at a velocity time graph. If this is my acceleration when I have the cart like this, with the wheel sides down, Peyton, what's going to happen to that velocity time graph when I flip it over and I push it like that? Will it be more steep, less steep, or the same?
Less steep.
Yeah. That's going to become a much smaller positive acceleration because of the fact that I had to pay so much more money to the friction mafia. Now, I take this and I push it at a constant velocity. So if I push it at a constant velocity, what's my net force going to equal?
0.
0. Because I'm still moving, but all the forces add up to equal to 0. Now, I want you to think this through. I push this cart at a constant velocity, and then I stop pushing it. As soon as I stop pushing it, what does it begin to do?
Slow down.
Begins to accelerate. Because what have I lost? When I stop pushing it, what have I lost? My applied force, my opposing force, or my net force? Lost my applied force. The frictional mafia is still there. Frictional mafia is going, hey, we're going to make you slow down. So when I stop pushing it, my applied force goes to 0. I still have an opposing force, but then I have a negative net force, which is going to make it slow down. Imagine this is a rocket. I'm going to fire the rocket engines, right? I'm going to have a positive net force that's going to accelerate upward. Now, as soon as I want to fire this up, but then I'm going to shut off the rocket engines. So shutting off the rocket engines is like me throwing this thing up in the air. As soon as I shut off the rocket engines, what's the only force left acting on that rocket? Gravity. So here's the story. And you can look at this a couple of different ways. Okay? Force applied, force opposing, force net, right? So when I'm firing the rocket engines, okay, there's my rocket engines being fired, right? I have a big positive force applied. I have some negative opposing force, and I have a positive force net, which is making this thing accelerate upward. And my velocity time graph is going to look something like this, right? My applied force is upward, it's bigger than my opposing force, I'm accelerating, boom, here you go. Now, at this point, I'm going to shut off the engines. If I shut off the engines, so then my engines go silent. I have no engine. What's the value of my applied force at that point? Do not make this difficult. 0. I have no applied force. Is the Gravity Mafia still working? Yeah. So once I shut off the rocket engines, what's the value of my net force? The same as my gravitational force. So these numbers are going to be the same. So that's why I said, every problem that you have, you start with this idea from here on out. From here on out, you start with this idea that applied plus opposing equals your net force. You start with that. And if you come up and you say, hey, Mr. Burkamp, I don't know how to do number 6. I'm going to ask you 2 questions. Have you drawn a diagram showing all the forces acting on it, and have you drawn a chart? And if you answer no to either one of those questions, I am not going to help you. Okay? True story. Because if you don't know what the forces are, and you don't know which direction those forces are acting, you can't solve the problem. Okay? Now, if you say, hey, this is what I have, I'll look at it and go, oh, that's a good start. Maybe we need to tweak some things. But if you come up to me and you say, I don't know how to do number 6, and if you haven't drawn a picture and have this chart, I'm not going to help you, because you at least have to get an idea of what's going on. Okay, so stop that. Okay, so let me get you started on this. So on number 1, you've got this large semi, and it's driving down the road. You have the mass. It's traveling at 108 kilometers per hour, and this thing is going to be brought to a stop. You need to know how much force is required to make that happen. So here's the story. So here's the semi. Okay, boom. Oh, this big trailer. Boom. Okay, like this, right? It's going down the road. That direction. You're going to hit the brakes. So start with this idea. You hit the brakes. What are the 3 forces acting on that semi at that point? Mr. Fisher.
You got force friction still.
Which is going which direction?
In the reverse direction.
Okay, so I've got my frictional mafia that I have to pay off.
Mm-hmm.
What else is there?
You still got force gravity.
I do have force gravity. And what else do I have?
Force natural.
Normal.
Normal.
Okay, force normal. Now, I'm asking you to find an acceleration. So right away, what do you know does your net force not equal? 0. So if you come over here and you draw a chart, you're going to go force applied, force opposing, force net. I'm hitting the brakes. I have no applied force. Okay? I'm not pushing the cart at the same time I'm hitting the brakes. I'm just hitting the brakes. There is no applied force. The only force that's going to make that thing accelerate is that force friction. Now, so if I find my net force, then I've found my opposing force, because they have to be the same thing. And only, and listen to me, 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 listen to me. Out of all the forces we're going to study, what makes net force unique is that net force, and net force alone, is the one that equals mass times acceleration. Okay? None of the other ones do. It's unique. Only one that equals mass times acceleration. So if I can find the acceleration of the semi, multiply that by the mass, then I have my net force, which means I also have my opposing force. Now, what variable is missing from problem number 1? What variable do you not have in your kinematic equations? Time. So what are you going to use? That equation. What are you going to do with 108 kilometers per hour? Change that into meters per second. 108 kilometers per hour. 108 has how many significant digits? 3. Your mass has 3 significant digits. Guess how many significant digits I want in that force? 3. Now, when you get to question 3, force of 16.4 newtons is applied to a 6.5 kilogram at a constant velocity. What are the 2 most important words in problem number 3?
Constant velocity.
What do you want your net force to equal?
0.
What are you going to make the forces add up to?
0.
There you go. Now, when you get to number 4, a force of 18 newtons is applied to a 1.5 kilogram box at rest. What's the acceleration of the box? So, here's the story on number 4. Number 4 is the easiest problem on the entire assignment. So, all you have is that here's a box. You're going to apply 18 newtons of force to it. You cannot, so that's it. You're just going to make the box accelerate. So that 18 newtons is your applied force, but you don't have any information that allows you to calculate the opposing force. So on 18, that force applied is also your net force, because you don't have any information to figure out what's working against it. So on number 4, literally, all you have to do is to get that acceleration, take the 18 newtons and divide it by the mass. That's all you have to do. So number 4 is the easiest problem on the entire assignment. Now, when you get to number 5, it's the exact same 18 newton force. This is the exact same 18 newton force. But now I'm telling you that the coefficient of friction is 0.4. Find the frictional force acting on the box. So on that one, you got to go, oh, force friction equals mu times force normal. So this is how the frictional mafia figures out how much money they're going to get. The frictional mafia goes, oh, I'm going to take mu, which is the coefficient of friction. I want to multiply that by force normal. That's how I'm going to figure out how much money I get paid. Now, when you get to number 6, on another sheet of paper, you're going to draw 2 diagrams to scale. Okay, these are not sketches, these are exact diagrams. So what's going to happen on number 6? You're going to have a box like this, and you're going to draw, okay, here's my gravitational force, here's my normal force, here's my force applied, here's my force friction. Done? Okay. So, you're going to draw that to scale. Okay? And some of these numbers are going to be pretty big. Huh? It's all scribbles, but you know what I mean. There you go. So, this is drawn, again, with a ruler, okay? You're going to set up a scale, maybe 2 centimeters equal Newton, maybe 3, whatever you want to do. Then you're going to draw this thing tip to tail. FG, here's some force applied, here's some force normal. Now, here's the whole point. What you'll see is that your frictional force is less than your applied force. That's what allows it to move. That's the whole point of this, okay? Because if my applied force is less than my frictional force, nothing's going to move, okay? So my applied force has to be bigger. Now, this harkens back to the days of vectors. Oh, I'm going to draw a net force. That net force is that resultant, and that's what you're after. When you get to number 10, here's a rocket. going to launch the rocket up in the air. You're going to have some force applied, you're going to have some force opposing, you're going to have some force net. When you get to H on the back side, you have to draw a velocity time graph for the motion of this rocket. Keep a running clock, okay? Keep a running clock. If your numbers don't fit on this graph, like let's say, for example, you get a velocity of, say, 400 meters per second. Don't sit there and go, man, Burkhamp is old, man, he's lost his edge. Man, this doesn't fit on the graph. Burkhamp screwed this up. No, Burkhamp did not screw this up. If your numbers don't fit on this velocity time graph, you have done something wrong, okay? Now, when you get to E on that back side, we're going to fire the rockets for 12.6 seconds, and then we're going to shut off the engines, okay? Throughout this whole thing, you're going to have to draw velocity time graphs. You're going to have to draw motion diagrams showing velocities and accelerations. Pay attention to the things that I want done in terms of all of these diagrams. Okay, I'm done running on. Fly, be free.